Okay, so as promised, parallel axis theorem example. So let's go through the setup. We have our sphere, and the center of mass of the sphere is located at point C. We have this arbitrarily set up basis, which we say is fixed in G, where EX points this way, EY is this way, and EZ is that way. We also have this point A, just out here in space. It's a body fixed point. It's located by vector RA. That locates point A. And we also have RB, which locates the other body fixed point B. RAC, that is just A with respect to C. That is 3EX plus 4EY plus 5EZ. Right, so that just means we go 3 in the EX, 4 in the EY, and then 5 in the EZ. That locates point A. And then similar thing for RBC, that is point B with respect to C. So we go 2 in the EX, and then minus 3 in the EY, and then minus 1 in the EZ. Just position vectors locating our body fixed points with respect to the center mass. The radius of our sphere is 0.5 meters, and the mass of our sphere is 10 kilograms. Objective. So first we want to write down the inertia tensor matrix at point C in basis G. Then we want to find the inertia tensor matrix at point A, represented in point G. And then from A, so assuming we only have information of the inertia tensor matrix at A, represented in G, we want to find the inertia tensor matrix at B, represented in G, right? So we talked about this last video. We're going to have to go from A to C and then C to B. And we'll talk about that. So at B, okay, and the fourth thing we want to do, at B, so once we have that matrix here at B, we want to rotate the coordinate system by first 90 degrees about the one axis, and then 45 degrees about that new 3 axis, right? So we're doing 2 rotations. And we'll be using Euler angles for that, which we've also talked about quite a bit, to come up with our direction cosine matrices. Okay, step 1. We're doing this right here. Step 1. Write down ICM. So this is, and this should be a little clearer, this should be G. So the inertia with respect to point C in G. So for now, let's just assume this is something we're given. I will go through maybe how to actually derive these inertias in a different video, but for right now, this is just something you can kind of look up for a sphere. It's a simple enough shape, but this is the inertia with respect to the center of mass of a sphere. It's zeros on the off diagonal, and then 2/5 mr squared on the diagonal, and they're all the same. Since the mass is distributed evenly, it's symmetric. Symmetric about that point. So this is just plugging in. This is just plugging in our mass and our radius, and we end up with 1s on the diagonal. That's it. 1 kilogram times meter squared on the diagonal. All right, that was part 1. That was easy. That was just plugging in to a matrix that we were given. Now we want to find IA represented in G. So this is just plugging into our equation that we did in the previous video, right? And I'm flipping back to the notes from the previous video. That is going from the center of mass. We're plugging into this right here. Going from the center of mass to some arbitrary body fixed point P. In our case, it's point A. But yeah, we're just plugging into this. So I'll talk through it, but it's really nothing special. So this is our position vector that goes from C to A, right? This is this vector right here, right? We're going from here to here. And we'll just plug in. So 1, 1, position 1, 1. This is equal to location 1, 1 in at C times M times R2 plus R3, both from squared. It's just plugging in. I don't really know what else to say here, right? So it's gonna be 1, which is this right here. I don't know why I wrote it like this, but 2/5 times 10 times 1/2 squared. That's gonna just be 1 plus 10 kilograms, which is the mass, times R2, that is 4 squared, and then 5 meters squared. This M here, this is meters, this is units, right? This isn't mass. So meters squared. So that's 16 plus 25 will give you 41, and then 41 times 10 is 410 plus 1, that's 411. 411. Okay, and then we do the same thing for the next one, except now we plug in R1 and R3. So R1 is 3 meters squared, and then this is going to be 5 meters squared here, so that's going to be 25 plus 9 is 34 times 10 is 340 plus 1 is 341. Yeah, again, I'll do one more, but it's really all the same, right? R1, R2, so R1 is 3, and then 2, R2 is 4. So 16 plus 9 is 25, times 10 is 250, plus 1 is 251. Right, and then these here are the off-diagonal terms. The C component is the I12, I13, I23 in the about point C. These are all just 0, right? And if we look back up here, that's these terms right here. Those are all 0. And then we're just plugging in our R's, and we get these values. Right, okay, so this is the answer to part 2 of our problem. The inertia tensor matrix at point A, represented in G, is this right here. All right. We're going to go a little quicker through this because I don't want to talk through just plugging in numbers. That's kind of boring. And I'm sure you don't want to listen to me do that. So 3. So from A, so we're assuming we only have this matrix that we just found, right? The information at A. And we must get to B. Remember, there is not a parallel axis theorem formula that will take you directly from some arbitrary point to some other arbitrary point. Does not exist. You can't do that. You can't go directly from A to B. You first have to go through the center of mass, right? So we're going to go from A to the center of mass, and then we're going to go from the center of mass to point B, another arbitrary point, right? So going from A to C, this is going from an arbitrary point to the center of mass. And if we look back at our equation, going from this one, going from some arbitrary body fixed point to the center of mass, we're going to use this set of equations to go from A to C, which is exactly what we do here and on the next page. Keep in mind, our position vector changes. It is now negated, right? Before we were going from C to A, now we're going from A to C, right? So it's negative of RA is the position vector, right? We're going from A to C this time. So that is what I've written here. R of C with respect to A is equal to negative R of A with respect to C. So we just throw a negative on these, right? We're going from A to C now. And it's the exact same thing. I'm not going to talk through it. We're just plugging in. I will let you pause here if you want to look at it and work through it on your own. I encourage you to. And this is the rest of the work right here. Again, I encourage you to do it. It's good practice. Okay. Good. And you'll see we end up with 1s on the diagonal. Does that make sense? Well, yeah, because, right, that's what we started with. That was the inertia tensor matrix at point C in G, right? And if we scroll back up, you'll see, when we plugged in our values here, we got 1s on the diagonal, right? We're basically undoing what we did before, right? So 1s on the diagonal, it's correct. That is this here. So now we're back at C. Now we're at the center of mass. Now that we went from A to the center of mass, now we're going to go from the center of mass to B. Now, this is the set of equations we're going to use for that, because these are the equations that are for going from the center of mass to some arbitrary point. Now we're going to use this. The only difference, again, I said this before, but the only difference between these two equations are these signs here. They're opposites. Okay. So going from C to B, we have our position vector that locates point B with respect to C, which we talked about before. And I'll show it. I'll show it. That is this vector right here, right? This is the vector that locates point B with respect to C, right? And it's right here, 2, -3, -1. 2, -3, -1. And we're just plugging into the equations for going from the center of mass to some arbitrary point. Again, I will pause here for a second, let you pause the video and work through it on your own. It's pretty straightforward. It's just plugging in. And I'm going to keep going. But what you end up with is this right here. So we did it. We did it. All right, we found the inertia tensor matrix at point B represented in basis G. Last part. At point B, we're going to now rotate the coordinate system by 90 degrees about the 1, and then we'll do a 45-degree rotation about the new 3, right? So it's going to look something like this, right? Right now, we're right here, and we have our inertia tensor matrix represented in that orange frame. So we're going to do 2 moves, right? First, we're going to do 90 degrees about the 1, right, which will bring EZ to point to the left. EY will now point in the direction of EZ, and then EX stays the same because we rotated about the 1. Right, so this purple one is the result of this 90-degree rotation about the 1. And then now this 45-degree rotation about the new 3. So we're rotating about this new 3, this purple EZ. That will swing up this EX to be in this UX direction. And it will swing down this EY, back in that XY plane to be this UY back here. And UZ and EZ point in the same direction because we rotate about the 3, right? So it'll look something like that. It doesn't really matter because we know the rotations. And I'm going to say this is fixed in F. This is fixed in F, this blue one. So we talked about DCMs. Go back and watch a DCM video if you don't know how these work. But this is where we were. This is where we're going. And we have to multiply in the reverse order of the rotations we do, right? So this is the first rotation. This is the second rotation. The first rotation, we're doing a fundamental 1 rotation by 90, followed by a fundamental 3 rotation by 45 degrees. First rotation, second rotation, where we were, where we're going. All right. So plugging in, we're plugging in to our, fundamental 1 and fundamental 3 rotation matrices, which we've derived in previous videos. I encourage you to go look at those. And if we use our unit circle and we compute this final rotation matrix, we'll get this right here, right? And the notation I'm going to use is C. The double underbars mean it's a matrix, right? A single underbar means a vector. 2 underbars means a matrix. So this is our fundamental. This is our rotation matrix to go from G to F, right? That's what we did. We went from G to F by doing these 2 rotations right here. All right. So I'm also not going to go through this, finding the inverse of a matrix, but that is what we need to do, right? We have to find the inverse of this rotation matrix right here because I'm flipping back to the other set of notes from the previous video. This is what we have to plug into, right? We have this already. This is our rotation matrix to go from one frame to the other. Then we also need the inverse of that. We need the inverse of that. So I will let you pause on this if you want to work through it. There's plenty of videos talking about how to find the inverse of a matrix of a 3x3. It's pretty common, but that is my work for that. And right here is our inverse, our inverse of that matrix. So now I'm just plugging in. That's it. So this is the fundamental rotation to go from G to F. This is going to be the inverse of the fundamental to go from G to F. And this in the middle is our inertia tensor matrix at point B in frame G, right? So what we're changing is this frame we're representing in, right? We're going from G, and now we're representing it in F. And you just plug in these matrices that we already have, that we've already found, and you'll get your final answer here. So this is our inertia tensor matrix at point B represented in this frame F. All right, we did it. Okay, that was a really good example. Now I want to show you this little Python tool that I created, this little GUI that I made that does all these calculations for you. So let's hop over to Python and go take a look at that. Okay, here we are in Python. This is the tool I was talking about. So if I run this script, it will come up with this. I know, very fancy, right? This is great GUI, great interface that we can use for basically all of the calculations we just went through. If you're curious, I made this using this program Qt Designer, and so it's just a drag and drop thing. You lay out your GUI. I exported the Python code and then just added functionality to it. And so if you go to the GitHub, there'll be 3 files in there. There is this .ui file, and that is what you can open in Qt Designer to see this interface. There's this parallel axis underscore GUI.python, and this is when you export the Qt Designer as a Python script, that is just the Python version laying out everything, laying out like all of the formatting and everything. But this is the one you're going to actually run, this parallel axis.py. That is what you actually execute, and it references this underscore GUI one to kind of lay everything out, and then parallel axis actually has all the functionality in it. So you're going to run this parallel axis one. So that's what I've done over here. So I just hit run, and it comes up with this. And now let's go through the problem so I can show you how this works. It's very basic. This is the first time I ever really used this like interface thing, so it kind of looks pretty bad, but it does the job. Okay, so part 1, actually we're going to do part 2. So we want to find the inertia tensor matrix at point A represented in G. So we're going to first, we go to this setup tab. There's 3 tabs on the top: setup, parallel axis, and then basis change. So you go to setup and you put in your current inertia tensor matrix. And you will notice that we only have, the lower half of this. And that's because, this element here, this element, and this element, the inertia tensor matrix is symmetric. It's symmetric. So, these are going to be the same, these are going to be the same, and these are going to be the same. So we don't need to waste time filling these out. So I'm just going to fill it in. So it was just ones on the diagonal. So ones on the diagonal. That was what it was at the center of mass. And then the mass we said was 10 kilograms. And you'll notice we have a message window down here. And the only functionality I have in here is if on the diagonal you put in, say, a negative number, say I put in -1, and you click away, it'll give you an error. It says error. You cannot have a negative number for I11, I22, and I33. You can't. That's physically not possible, right? So it's just help you avoid an error. So we'll put in 1 there. And that's all the setup you need. Current inertia tensor matrix and the mass. So now we go over to parallel axis. And looking back at our problem, our vector that pointed from C to A was 3, 4, 5. So I'm going to put in 3 for R1, 4 for the second element, and then 5 for the third element. And then we have these radio buttons here, and we are going from the center of mass to some arbitrary body fixed point. So yes, that's what we're doing. This is not editable here. This is just showing you what our current tensor matrix is. And then our new tensor matrix will be calculated when we hit calculate. So calculate. And this matches what we had before. This is the exact same thing we calculated by hand. Okay, great. So that took us from C to A. So now, say we're at A. So say we're at A. So I'm going to fill in that matrix here. So 411, 341, 251. Whoops, 251. And then the off diagonal is -120, -150, and -200. Mass stays the same. We're going to do parallel axis. And this time we're going from A to B, right? But first we have to go through C, right? You can't go directly between two arbitrary points. So we're going from A to C and then C to B. So we're going from A to C. So we're just going to negate these. Negative. Negative. And we're going to change our radio button, right? Because we're going from some arbitrary point to the center of mass. We hit calculate. And now we're back at the center of mass, right? 1, 1, 1. Great. Now that we're at the center of mass, so I'm going to change these back. And now we're going to go to point B. We're going to go to point B. So I'm changing this back to we're at the center of mass. I'm going to hit parallel axis. And the position vector that goes from C to B was 2, -3, -1. So 2, -3, -1. And now we're going to change this button again. So we're going to go from the center of mass to some arbitrary bodied fixed point. We're going to hit calculate. And I am looking at our notes to see if this is the same thing we got. 101, 51, 131, 60, 20, -30. Okay, so it worked. So we are now at point B, represented in frame G. And now the last thing we did was a rotation, right? We applied the rotation matrix to represent it in some other basis. And so let's go ahead and do that. So setup. We go back to the setup tab, and we're going to put in our current matrix. And right now we're at B represented in G. So I'm just going to put in that matrix we're in right now. 101, 51, and 131. And then the off diagonals are -30, 20, and 60. Mass is the same. And then we go over to this basis change tab. And now we have to put in what our rotation matrix is. So what is the rotation matrix that goes from G to F? I just need to know what square root of 2 over 2 is. It's like 0.7 something. Square root of 2 over 2. Okay, it is this number. I'm just going to copy and paste it. Copy. And our rotation matrix was root 2 over 2, negative root 2 over 2, 0, and then 0, 0, -1, and then root 2 over 2, root 2 over 2, and 0. Okay. I just copied this from our notes. And I'm going to hit calculate, and this is exactly what we got before, doing it by hand, right? 136, 96, 51, 63, -21, and 15. Okay. That is the tool. It's available on the GitHub. Have fun. Go crazy with it. And I'll see you in the next one. Bye.